Okay, so our start of this semester, chapter 14, focuses on solutions. Okay? Solution chemistry is a really important aspect of chemistry. There's like no doubt in my mind that throughout your, just in 1A lab, you were using some solutions in the lab. It turns out that like solids don't really react with one another very well because those molecules and atoms are kind of frozen in place, right? Solution chemistry is a really popular form of chemistry because everything's in this liquid state moving around where there can be interactions between different molecules. I myself was a biochemist. That's what I got my PhD in. I spent 10 years only doing solution chemistry, okay? Us, if you have any interest in biology, we are essentially just bags of solution, right? Our blood is nothing but a solution with a whole bunch of different proteins and fats and sugars and all that other stuff floating around in it. So especially specific to life, solution chemistry is really important. All right, so first thing we got is some terminology here. So first, what do I mean by a solution, right? Let's say that I take some table salt, some sodium chloride, and I dissolve it in water. To create salt water. That salt water that I've created is a solution. Okay? Strictly speaking, a solution is just a homogeneous mixture of different molecules, different compounds. All right? Some other terminology here. Let's say that I take sodium chloride and I dissolve it into water. The sodium chloride in this example is what we call the solute. Okay? And the water that I'm dissolving my solute in, we call the solvent. Okay? So a solute dissolves in a solvent to create a solution. All right, so again, we got some new terminology here. A solute, that's the thing that you're dissolving into your solvent to create your solution. All right, so I have a recipe here for simple syrup, which is the basis of many cocktails, where you take 1 cup of sugar and 1 cup of hot water, and you stir to combine. All right, in this example, in my recipe here, I want you to tell me what my solute is, what my solvent is, and what my solution is. All right, what's my solute? The sugar. And what's my solvent? The water. And then lastly, what's my solution here? The actual simple syrup itself, right? What you get at the end is your solution. Cool. Water is the most common solvent and probably the only solvent that you'll be using at this point in your chemistry career. When you go on to organic chemistry, you'll be introduced to many organic solvents, but typically speaking, at this level, water is the most common one. Okay? All right. So another phrase that we're going to have that we sort of keep in mind that you may have heard is like dissolves like. Okay? This is this just very simple phrase that people have in their mind when they're preparing solutions, and this is sort of a shorthand for the idea that a polar solute will dissolve in a polar solvent and likewise a nonpolar solute will dissolve in a nonpolar solvent. But polar and nonpolar don't mix. Okay? So if you took a polar solute and you tried to combine it with a nonpolar solvent, it would not dissolve. So a nonpolar solute will not dissolve in a nonpolar solvent, and vice versa. I ran out of room. All right, so this is what we mean by like dissolves like. Polar will dissolve in polar, nonpolar will dissolve in nonpolar, but the two don't mix. All right? And maybe we should remind ourselves real quick, what the heck do I mean by polar and nonpolar? All right? So polar quite simply means that you have a molecule where there's an unequal distribution of electrons within that molecule, right? So polar means unequal distribution of electrons. All right, so a good example of a polar molecule would be HF. All right, if we sort of looked at where the electrons were living in this molecule here, we would see that a whole bunch of electron density sits on that fluorine, and the hydrogen doesn't have much electron density at all, right? So there's an unequal distribution of electrons. Part of this molecule has a bunch of electrons. The other part is left relatively electron deficient. And what do we know about electrons and their charge? Holy hell. What is the charge of an electron? -1. Excellent. So if we have this unequal distribution of electrons here, we have a whole bunch of negative charge sitting on one end of this molecule, and that leaves the other end partially positive charged. All right, so this is what it means to be polar, is to have this unequal distribution of electrons. Some electrons live in one part, giving it this partial negative charge, and they're absent from another part, giving it this partial positive charge. Okay, this little fancy symbol here, this lowercase delta, this means a partial, in this case, negative charge. Okay? All right, so we're going to sort of explore this, come back to this idea of like dissolves like here in a second, but now we got to talk about what are called intermolecular interactions. All right? Okay? And that is a big, ugly, scary word, but let's just pick this apart real quick. Intermolecular, that means the intermolecular interactions. That means the interactions between neighboring molecules, right? So we have this solution that has, 10 to the 23 different molecules floating around. What are the interactions between neighboring molecules, right? So that's what we mean by intermolecular. Okay, so now we're going to learn about a few different types of intermolecular interactions here, the type of interactions that neighboring molecules have with one another. And what we're going to do is we're going to introduce them from the weakest type to the strongest type. Okay? So our weakest form of intermolecular interaction are what are called dispersion forces. Okay? Dispersion forces are the weakest of all the intermolecular interactions. Okay? These are the interactions between the surfaces of neighboring molecules. And all molecules are three-dimensional, right? They're super teeny tiny small, but they're these three-dimensional objects, so all molecules have surface areas. The interactions between the surface areas of neighboring molecules we call dispersion forces. Okay? So these are this force of interaction. All molecules have them, but they're very, very weak. All right? Importantly, we also want to note about these dispersion forces here. Nonpolar molecules only have dispersion forces. So we're going to learn about a few different types of intermolecular interactions that are stronger than dispersion forces, right? But if you're a nonpolar molecule, the only type of interaction that you have are these dispersion forces here. So nonpolar molecules only have dispersion forces. All right, and since we're sort of talking about nonpolar molecules, let's also make a note here that CH bonds are nonpolar. Okay? All right, so these are our weakest intermolecular interaction, these dispersion forces that just arise because I got these two 3D objects. They have surfaces. Those surfaces are going to interact with one another, right? But they do so very weakly. So now we have some stronger forces here. Our next level up is what are called dipole-dipole interactions. Okay? These are stronger than dispersion forces. But not all molecules have dipole-dipole interactions. What type of molecules don't have these? Because they only have dispersion, the nonpolar, right? So this is then the next level up, but this is only found in polar molecules. Okay? So let's go back to our example here of HF. That's actually a bad example. Okay, another example will be this molecule here. This is formaldehyde. I don't know if you guys have ever taken a biology course where you did any dissection, but you would have worked with this extremely stinky compound here, formaldehyde. This is the structure of that molecule. Okay? And this is another example of a polar molecule. This oxygen here has a bunch of electron density sitting on it, leaving it with a partial negative charge. This carbon over here is left relatively electron deficient and thus has a partial positive charge. Okay? This is what we call a dipole in this molecule here. When one portion of the molecule has partial negative charge, the other portion has partial positive charge, that's what's called a dipole. Right? And these are dipole-dipole interactions. So if we take a polar molecule like formaldehyde, it can interact with a neighboring molecule of formaldehyde through these dipole-dipole interactions, where the partial negative end of one molecule is talking to the partial positive end of its neighbor. Right? What do we know about opposite charges? They attract one another. We have this portion of a molecule that's partially negatively charged. It's going to interact fairly strongly with the portion of a neighboring molecule that has a partial positive charge. Okay? So this is this dipole-dipole interaction. Okay, the partial positive end of one molecule interacting with the partial negative end of its neighbor. Okay? So now importantly, how did I know that this molecule right here was polar or that HF was polar, right? How can I spot when I have a polar molecule? Okay? So this goes back to this concept of electronegativity. And I know everybody did nothing but study chemistry all summer long, but let's review electronegativity so we can make sure to sort of understand what we're talking about here. For that, we want to look at a periodic table. So let me find one. I got one around here somewhere. Okay, ignore all this. So, electronegativity, strictly speaking, if we're going to define it here, this is an element ability to pull electron density in a covalent bond. Okay? So, you learned about different types of bonding. Covalent bonding, you learned, was the sharing of electrons between two atoms. Hopefully that word sharing is kind of synonymous in your mind with covalent bonding. Right? And sharing sounds like it's this nice, neat, like gentle experience going down. Really, those atoms are involved in this epic tug-of-war battle for those electrons, right? Both of those atoms are holding on to those electrons, and they're kind of in like this tug-of-war over that pair of electrons that's bonding them together, all right? It turns out that certain elements are way better at tug-of-war than other elements, and the tug-of-war champion is fluorine. Okay, the most electronegative element is fluorine. If you are in a bond with fluorine, it has pulled all that electron density from that bond onto itself. Okay, and the closer you are to fluorine on the periodic table, the more electronegative you are. So everything trends towards that tug-of-war champion fluorine. Okay? So then how can we spot that we have a polar bond? Right, we said that our HF, this was a polar bond. Polar bonds will occur between elements of differing electronegativity. Okay. So, a carbon-oxygen bond, is that going to be polar? Are those two elements of differing electronegativity? Yes, right? Oxygen's much closer to fluorine than carbon is, so the oxygen in these bonds is pulling that electron density away from the carbon. What if I have a carbon-carbon bond? Is that going to be a polar bond? No, they're the same element, right? One can't be better at pulling electron density than the other. Okay? And then importantly, what about a carbon-hydrogen bond? Remember, these are the ones that we say are always nonpolar. Okay? Organic, there are a lot of molecules out there that exist only of carbons and hydrogens. It's what's called organic molecules, so we'll see a few examples of these. But yes, they are nonpolar if all they have is carbons and hydrogens. Cool. All right. Next level up is what we call a hydrogen bond. Okay? And a hydrogen bond is actually just another example of a dipole-dipole interaction, but using a specific combination of atoms. Okay? So this is just, again, an interaction between polar molecules, a dipole-dipole interaction. All right, but specifically when those molecules contain one of three bonds. It's got to be one of these three bonds to be a hydrogen bonding molecule. Oxygen, hydrogen, nitrogen, hydrogen, and fluorine and hydrogen. All those very electronegative elements paired with hydrogen. So these are the only 3 types of bonds that can engage in that next level up strength of dipole-dipole interaction, which we give its own special name, hydrogen bonding. Okay? So if we just want to look real quick, it's again going to look very similar to our dipole-dipole interactions. Like the classic example of a molecule that exhibits hydrogen bonding would be water. Right? So if we take a water molecule, it's again got that polar bond, so it's got a partial negative charge on the oxygen and a partial positive charge on the hydrogen. And so if we have a neighboring water molecule, the partial negative end of one will align itself with the partial positive end of the other. Okay, but again, the interactions, that dipole-dipole interaction is taking place between one of those special something in hydrogen bonds, oxygen and hydrogen, right? So again, we would call this, these are both dipole-dipole interactions. This is dipole-dipole because it's carbon-oxygen. That wasn't one of our 3 special. And then this one is that next level up in terms of strength of interaction, which we give its own special name, hydrogen bonding. Okay? Our last intermolecular interaction here, and the strongest of all of these forces that we've discussed, is an ion dipole interaction. Okay? So we talked about how the partial positive end of one molecule likes to line itself up with the partial negative end of the other molecule, right? The only thing better is if instead of having a partial negative charge, you have a full-blown negative charge or a full-blown positive charge, right? We call those ions. So, again, this is our strongest of all of our intermolecular interactions. And if we see here, we have this sodium ion, right? It's an ion because it's got that net positive charge associated with it. And what we see pictured here are all these water molecules. The oxygen is pictured in red, the hydrogen's pictured in white, and you can see that all of these oxygens have turned around so that their oxygen butts are all aligned on that positive charge, right? The partial negative end of that water molecule is interacting very strongly with that net positive charge. Okay? The basis of all of these polar interactions here is just that opposites attract, right? The idea that negative charges are attracted to positive charges. Okay? And then again, if you're non-polar, you don't have any unequal distribution of electrons. The only thing you have is the surface areas of your 2 molecules interacting. And again, that's the weakest type of intermolecular interaction that you can have. Okay? So our ion dipole, if we just want to make note here, this is a charged ion interacting with the dipole of neighboring molecules. Cool? All right, so first thing we want to be able to do with this before we sort of move on, we're going to sort of tie this into this like dissolves like concept, right? We introduced that and then we beelined it and started talking about intermolecular interactions. We'll tie these 2 together, all right? But first thing that we want to be able to do is if I give you the structure of a molecule, you should be able to tell me what the strongest intermolecular interaction that they have are, okay? Now, again, all of them have dispersion forces, right? But what's the strongest? Is there anything stronger than that? Is there a dipole-dipole interaction, or is there hydrogen bonding? Okay? So I'm going to put down a few molecules, and you're going to tell me what the strongest type of intermolecular force is in those molecules. All right, so for this first molecule here, this thing's called ammonia. What are the strongest intermolecular interactions that would be present between neighboring ammonia molecules? So this one would be hydrogen bonding. Okay, and how can I spy that? Because it has one of those three types of bonds that can hydrogen bond, right? Remember, we made this list here. Oxygen, hydrogen, nitrogen, hydrogen, and fluorine and hydrogen, right? If you're on that list, you can hydrogen bond. So in this case, we had a nitrogen-hydrogen bond, so this can hydrogen bond. I know I just said hydrogen bond like 1,000 times. Okay. What about this one here? What does this molecule have? Does it have hydrogen bonding? No, right? Because I do have a hydrogen, but it's attached to a carbon. And remember, we said that those bonds were nonpolar, okay? But then what's the strongest type of force in this molecule? Dipole-dipole. Because sulfur is quite close to fluorine, carbon is a few tiles away, so I have this bond of differing electronegativity, right? Here's my partial negative end, here's my partial positive end. So this can dipole-dipole interact. All right, and what about this molecule here? So this has dispersion forces. This is a nonpolar molecule. It consists only of carbons and hydrogens. Okay? And then lastly, I actually got to complete this because it would be the interaction between these two molecules here. What is the strongest interaction that would take place between water and this thing right here? All right, so if you ever see that net charge, a naked charge on there, that's going to be the strongest forces, those ion dipole interactions, right? The ion of one molecule is interacting with the partial positive end, the dipole of its neighbor. Okay? Cool. So what the heck do these intermolecular interactions have to do with making solutions? This like dissolves like business. All right? Well, let's think about this. We're going to do like a thought experiment here. We're going to make a solution. Okay? Here's my solute. And then I got this beaker. With my solvent in there. And I want to combine these to make my solution, where I have my solute molecules homogeneously distributed, homogeneously, all right, so. Right, I got my solute molecules floating around in my solvent to create my solution. Cool? So, in order to create my solution, I'm going to have to first break the interactions between neighboring molecules in my solute. Right? So I got to take my solute and I got to break those intermolecular interactions. All right, so I have my solute, but now they're all separated out here. All of them have been broken apart. Okay? Now, likewise, I'm going to have to do the same thing with my solvent. All right, I got to make room for those solute molecules. So I'm going to take my solvent, and likewise, I have to break those intermolecular interactions between neighboring solvent molecules. Right? I got to make room for those solute molecules. Okay? In order to do this, in order to break those intermolecular interactions, I have to put in energy, right? These things aren't going to want to separate all by themselves, so I'm going to have to put in some energy to separate these molecules, to break those interactions. So these two steps right here, it's okay, we'll get there, all right? Now, both of these things right here, breaking these intermolecular interactions is going to require an input of energy. So these two steps right here require an input of energy. Okay? But now when I create my solution, right, now I have all these interactions broken. When we create our solution, now we're forming new intermolecular interactions. Right? So now I'm going to stick those solute molecules in between two solvents, and they're going to form new intermolecular interactions. Okay? And since we're creating these new interactions, that step will actually release energy, right? There will be an output of energy when those two molecules find one another. Okay? Cool. So, again, we're trying to tie this back to this phrase, like dissolves like. So let's just think about it. Let's take an example of two molecules that would not form a solution together. All right? We're going to combine a nonpolar solute with a polar solvent, our classic water. Okay? And again, this will not create our solution. So let's explore why that is here, based on what we just discussed. What are the strongest intermolecular forces present in this molecule here? Dispersion forces. Am I going to have to put in a lot of energy to break these dispersion forces? No, they're super weak, right? So I'm going to represent that with the height of this arrow here. These dispersion forces are quite weak, so I'm going to have to input energy to break them, but I'm not going to have to input very much. Okay? So these are our dispersion forces. And we're going to input a small amount of energy. Okay? Now I have my solvent, my water molecules. Actually, let's be good. This is my solute. This is my solvent. Again, I got to break those interactions between my solvent molecules. I got to make room for that solute in my solution. What are the strongest type of intermolecular interactions present in my water solvent? Let's look back. What are the strongest intermolecular interactions between neighboring water molecules? Hydrogen bonding, right? Are those strong or weak? Am I going to have to put in a lot of energy or a little bit of energy to break those hydrogen bonds? Kind of a lot, right? They're pretty high up on my strength scale here. So I'm going to have to put in a lot of energy to break those hydrogen bonds. We're going to call them H bonds for short. Okay. So now we said that like dissolves like, so my nonpolar isn't going to dissolve, but let's sort of see why that is here. So now on my solution end, I have this molecule interacting with water here. What's going to be the strongest type of interaction between water and this nonpolar molecule? Can these two hydrogen bond with one another? No, water can hydrogen bond with neighboring water molecules, but there's no hydrogen bonding potential with this C2H6 business here, right? So what's going to be the strongest interaction that we see between water and this nonpolar molecule? What's the only thing that nonpolar molecule can do? Dispersion forces. And like we said, these interactions will release energy, but is it going to release a lot of energy or just a little bit of energy? Just a tiny bit of energy, right? So I will get a release of energy, but a release of a small amount of energy. All right, because again, these are just dispersion forces. Okay, so the bottom line is it is not worth it for water to make room for this nonpolar solute. It would have to break some very strong interactions to make room for these very weak interactions. It is just energetically a loser, right? You got to put in way more energy than you're going to get out when this solution forms, right? So why do nonpolar molecules not mix with polar molecules? Why is it that only like dissolves like? Because you have to put in too much energy and you don't get back very much, right? Your return on investment energy-wise is not good, right? So why does like dissolve like? Again, just going back to that phrase. Because it requires, or let's actually say, why does like not dissolve unlike? Quite simply because you input more energy than is released. Okay? We're going to spend a lot of time talking about energy in this class. For right now, what you want to know is from the universe's perspective, it does not let things happen that require this net input of energy. The universe likes outputs of energy, so it's not going to let this thing occur. Again, it's an energetic loser. Okay? Remember, we said that when we create a solution, we're going to do this little thought experiment. The first thing that we got to do is we got to break those intermolecular interactions between our solute particles, right? So we got to separate them out from one another. Is this a process that's going to release energy or require an input of energy? To break them apart. We need to input energy, and I need to put in some energy to break those bonds that are holding those together, right? So we're going to see an increase of energy in this step. This symbol that we're going to use for energy is this delta H here. All right, and for right now, you're just going to, this is our symbol for energy that we're talking about. We're going to talk a lot more about this particular variable here when we get to our thermodynamics chapter. But this delta H is the energy to break up those solutes, okay? And we have a special name. We said it requires an input of energy, right? We have a special name for processes that require an input of energy. These are what are called endothermic processes. So this step of breaking apart the interaction between neighboring solute molecules, this step right here would be an endothermic step. All right, so now our solutes are all broken up. The next step was we got to do the same thing to our solvent particles. We also got to break those apart. This will also require an input of energy. So again, we're raising the energy here. Now our delta H is the delta H of our solvent, right? Because we're talking about breaking the solvent interactions between neighboring solvent molecules. Again, this requires an input of energy. And again, we got a fancy term for that in chemistry. That would be an endothermic process. Okay? So now we've got everything all separated. Separated out our solvent particles, separated out our solute particles. Now we get to mix them together, and we're going to form new interactions between the solute and solvent. Right? We had to break apart a bunch of interactions, a bunch of those intermolecular interactions we learned about. Now we're going to mix everything together and create a bunch of new ones. When we make new interactions, does that require an input of energy or does that release energy? That's the favorable step, right? That's the one that releases energy. So now, boom, our energy goes back down. And we have created our solution here. Okay? That mixing process releases energy. And of course, we have a special fancy name for processes that release energy. These are what are called exothermic. Okay? Now, you can see from this diagram here the amount of energy that we had to put in, right, to break those interactions between our solute and our solvent is less than the amount of energy that we got back that was released at the end, right? So the net result here of this mixing process is an exothermic reaction, right? Our solution that we created, the delta H of our solution is exothermic, right? We ended up releasing more energy than we had to put back in, so the net result is an exothermic process, okay? We talked a little bit about this before, and we'll talk even more about it when we get to thermodynamics, but the universe loves chemical processes that release energy, okay? So it turns out that all exothermic solutions will mix spontaneously. All right, meaning that you will indeed form a mixture. Okay? Now, let's say that we do this same thing here, but we use like a non-polar solute and a polar solvent. So at the end of the day, the amount of energy that we get back that's released by this mixing, all right, this arrow is going to stop somewhere up here. Okay, so the net result here would be what? Endothermic or exothermic? This would now be endothermic. I've put in more energy than is being released at the end of the day. So this would be a figure that would be a net endothermic solution. That is, my handwriting's too messy from that far away. Hold on. Okay. Endothermic solutions. Usually, and we're going to have this caveat here, usually do not mix spontaneously. This would be an example of, for, like we talked about before, a non-polar solute in a polar solvent. All right, it's not worth it for water to break its interactions with neighboring water molecules to make room for a non-polar solute. It doesn't want it there. It would much rather have those strong interactions between neighboring water molecules. All right, so that would be a net endothermic process. These are usually not spontaneous. Okay? There's one important caveat here, though. And we talked a little bit about this at the end of class. Some slightly endothermic solutions will mix. And does anybody remember that magical force that we talked about that would drive this mixture that would otherwise be unfavorable? It is the most bizarre force in all of the chemistry universe, that entropy, yes. So then the universe will let us get away with it sometimes, if it's ever so slightly endothermic, because the universe loves chaos. Because of the disorder that's created by mixing these two things, the universe is like, fine, I'll give it a pass, if it's slightly endothermic. Okay? Mix because of entropy. Okay, and for right now, I just want you to keep this in mind because, you know, in your lab, you may do a thermodynamics experiment and you may find that this solution mixes with a little bit of a absorption of heat, an endothermic solution, and you're like, wait a minute, he lied to us. That's not supposed to happen. No, this does happen when it's ever so slightly endothermic because of this concept of entropy. All right, and we'll do a deep dive on entropy here in a few chapters. Okay, what's up? No. So we're talking about strictly thermodynamically speaking, like even if I went in there and manually separated water molecules and stuck this thing in the middle, if it's not going to spontaneously mix, they'll kick it out and you'll form those two layers. A great example of an endothermic solution that does not mix would be oil and water. What happens when you put these two things together? They form two distinct layers. And you can get in there and put it in one of those paint shakers that just goes freaking crazy, right? And you let it sit for a little bit and it will absolutely separate back out. So we're talking about like infinite time scale. These things will still separate back out into their two layers. Okay? Okay. So now another important concept that we're going to talk about with regard to solutions is this idea of solubility. Okay? Because even favorable mixing events have a limit, right? Sodium chloride will very favorably dissolve in water. Nonetheless, you're not going to get a dump truck full of sodium chloride to dissolve in a thimble of water, right? There's going to be a limit somewhere that you reach. That limit is what we call the solubility of that substance, right? So solubility, this is the maximum amount of solute you can dissolve in a given solvent. Okay? This is a property that's unique for every substance, like densities or something like that. These are tabulated in, back in my day, these books that were like this big that you had to flip through. Nowadays, everything's online in these databases, right? But every compound will have its own unique solubility in a given solvent. Again, in this class, at this level, the most common solvent that we'll use over and over and over again is water, okay? So what I'm going to teach you guys how to use is this chart here. This chart has a lot of information, so let's sort of pick it apart here, okay? First of all, we have several different compounds that we can find on this chart, right? So it summarizes the solubility of several different compounds here, okay? Notice that those solubilities are listed in grams of solute in 100 grams of water, right? So every point on this graph tells you how much solute you can dissolve in 100 grams of water. Okay? And then the other very useful thing about this graph right here is that it gives it to us at a bunch of different temperatures. All right? Now, first of all, besides cesium sulfate, which is an oddball here, what happens to the solubility of a compound as we increase temperature? Solubility increase or decrease with increasing temperature? It increases, right? Sometimes, as in the case of KCl, it doesn't increase very much, very, very shallow curve. And other instances, it's a dramatic increase with temperature, right? And again, this is just something that's unique to each of these solutes here. Okay? So let's make sure that we can read this graph here. I'm going to ask you, let's say, what is the solubility of, let's do KCl at 50 degrees Celsius. Okay, everybody take a second. Let's read our chart here. All right, we got to find the KCl. That's this one here. We got to look on our graph at 50 degrees, trace it up. So I'm talking about this point right here. Okay? So this, we're going to say 42 grams of KCl per 100 grams of water. Now, that last digit, because of this graph here, I know it's between 40 and 50, right? That's very obvious because the line's on this graph. That last digit is what you would have learned about when you're reading instrumentation in lab, would be called like an uncertain digit. I looked at it and said 42. You might have looked at it and said 43 or 44. There's a little bit of wiggle room in that last digit, right? Regardless, any one of those numbers will get you in the same ballpark, okay? All right, so now, let's ask a slightly different question here. Let's say how much, we'll say how many grams, can be dissolved in, let's do easier numbers, 150 grams of water at 50 degrees Celsius. Okay, so my chart tells me how much will dissolve in 100 grams, but now I have a little bit more water than that. I have 150 grams. So how am I supposed to figure that out? We're going to pull that solubility value from our table, okay? And importantly, how we're going to use this, how we're going to build this so that we can use it in our math, is we're going to stack that 42 grams of KCl over 100 grams of water. Okay? This is going to act like a conversion factor. You would have learned last semester how to convert from, for example, inches to centimeters using a conversion factor that you built. We're going to use this in the exact same way. It's going to help us jump from units of grams of water to units of grams of KCl. Right? So if I take my 150 grams of water, I'm going to multiply it by that solubility. And how can I tell that this is set up correctly? My units cancel out beautifully, right? My grams of water cancel out, and so I'm left with what I want, which is grams of KCl, right? So this solubility that we get from our table here, it's not just a single number all by itself. We can build this little conversion factor here, okay? All right, and so if we punch that into our calculator, you get 61 grams of KCl. All right, cool. So there's some other fun stuff that we can do with this graph here because it gives us these solubilities at various temperatures. All right. There is in organic chemistry, well, it's mostly featured in organic chemistry. You do it in organic chemistry lab a lot, but I guess it's everywhere. This phenomenon, this purification technique called recrystallization. Okay? And the process here is pretty straightforward. You're going to dissolve a solute in a hot solvent. Okay? So we have our, let's pick a better one here. Let's do our potassium dichromate. According to my graph, if I raise my temperature up to 80 degrees Celsius, I can get about 57 grams of that potassium dichromate to dissolve in 100 grams of water. Okay, so we're going to heat up our solvent and dissolve some of our solute in there. All right, and then we're going to cool that solvent. All right, so if I take this and I cool this back down to, say, 10 degrees, up here at 80, I could dissolve 57 grams, right? So if I put 57 grams in there, and then I cool it down to 10 degrees Celsius, now my solubility has changed to 18 grams per 100 grams of water, right? So my solubility decreases when I decrease that temperature. Now the maximum amount that will remain in solution is that 18 grams. So what happens to the rest of it? It precipitates back out, right? It crystallizes. You guys would have done that alum lab where you grew those alum crystals, right? That's exactly what you would see. You would see these crystals of, in this case, potassium dichromate start to form back in your solution. Okay? And the reason that they do that is because those crystals that you get are more pure than what you started with. So it's this purification technique to get a really clean sample. All right, so we're going to cool our solvent back down. Our solute will recrystallize in a pure form. Okay, so we can play this same game but quantitatively using that graph, right? How many crystals how many grams of crystals would we actually expect to get back if we did this experiment? That's what the type of problem that we can do using that graph, since it gives us these solubilities at multiple temperatures. Okay, so let's just we'll pick a different one since we sort of went through this one. Let's do the potassium nitrate here. Okay. So everybody take a second. We're going to heat our solution up to our solvent to 50 degrees Celsius. What's the maximum amount of our KNO3 that we can get to dissolve? Everybody take a second and write down a number for me. Make sure we're reading this chart correctly. Right, so this point here, and again, there might be some wiggle room in that ones place. I'm going to say that's 88. 88 grams of potassium nitrate will dissolve in 100 grams of water at 50 degrees Celsius. Right, so we're going to dissolve 88 grams of potassium nitrate in 100 grams of water at 50 degrees Celsius. All right, step one, dissolve our solute in a hot solvent. Check, check. Okay? Now we're going to take this thing and we're going to throw it in an ice bath and we're going to cool this down to 0 degrees Celsius. All right, so step 1, how much of our KNO3 remains in solution? Okay, so everybody take a second and see if you can't answer that. How much of that potassium nitrate is going to remain in that solution at 0 degrees Celsius? All right, I'm going to follow this graph back down all the way to 0 degrees. Okay, I'm going to say that's 13. So how much remains in solution? 13 grams of KNO3. All right, because that's what a solubility is. It's telling me how much is in my solution, the maximum amount. And then what we really care about is how much KNO3 has recrystallized. How the heck am I going to figure that out? Somebody said it. What operation? Subtraction, right? I got my 88 grams that was initially in my solution. There's 13 grams that remain. So that difference, that 75 grams, is how much has recrystallized. Okay, and again, the whole shtick is like, yes, I lost a little bit of my sample. I started out with 88 grams, now I only have 75, but those 75 grams are nice and squeaky clean, pure, awesome, right? Cool. So because we have our solubilities and we have them at multiple temperatures, we can predict the results of these recrystallization experiments, right? Where again, we start out with our solvent at a high temperature, dissolve a whole bunch of solute in there, and then cool it down, and we can calculate how much has recrystallized out. "150 grams of that potassium nitrate is dissolved in 225 grams of water at 50 degrees Celsius. This is then cooled to 0 degrees Celsius. How much KNO3 recrystallizes? All right, so I'm going to give you guys a bit of a head start here. Try to answer this one on yourself, answer this problem by yourselves, and then we'll do it together. Okay, and one of the things you want to do first is to check, did all 150 grams of your solute that you put in there actually dissolve? All right, so make sure to check for at that 50 degrees Celsius. What is the solubility of that KNO3 in that 225 degrees of water? Make sure we didn't accidentally add too much of our solute here. All right, so we're talking about our KNO3 at 50 degrees, and we'll also need this point here at 0 degrees. I'm gonna call this 88 grams per 100 grams of solvent, and this is looking to me around 13, maybe 14 grams per 100 grams of solvent, okay? If you use values that were like 1 or 2 off, that's fine. You'll get about the same right answer. All right, so 88 grams of KNO3 per 100 grams of water. But I have 225 grams of water, right? So I want to set up my calculations such that my units will cancel out, grams of water cancel out. Okay, and that 88 times that 225 brings me to 198 grams of KNO3. So did all my solute dissolve or no? All right, remember what this value is. This is the limit here. This is the upper limit of how much potassium nitrate I can get to dissolve in my solvent, right? If I put less than that, then yes, all of that 150 grams will indeed dissolve. If I put 200 grams in, what would happen? What would I be left with? There's those 2 grams that didn't get dissolved, right? So it's like I would put a big old scoop in and I would still see some solid left floating around. All right, so we're gonna check to make sure indeed all of those 150 grams dissolve. Check, check. All right. Now we got to go and we got to figure out what the solubility is at that 0 degrees point. Said it was 13, so this was 50 degrees Celsius. At 0 degrees Celsius, whoops, it's 13 grams of KNO3 for every 100 grams of water. All right, and again, we have that 225 grams of water. Set it up such that our units cancel out. And we get 29.25 grams of KNO3. Right, and remember that's how much will remain in solution after you've cooled this down, right? That's my solubility, that's the upper limit of what will dissolve. So in order to get how much has recrystallized out, I'm going to do that subtraction step at the end, right? I'm going to take my initial value, my 150 grams, and I'm going to subtract that 29.25 grams, because this was my initial. This is how much remains in solution. So the difference there, that 120.75, this is how much recrystallizes. All right, if we're being good with our sig figs, 121 grams. Okay, so from this chart, I can figure out my solubility at my different temperatures. I have to adjust for the amount of water that I'm actually using, right? This table tells me what it is at 100 grams. I had to adjust for my 225 grams of water, okay? I can figure out the solubility at each temperature, and then by taking the difference there, I can get how much has recrystallized at the end of that experiment. All right, so every one of these compounds on this table here are ionic compounds. They're solids. You would mass them out in the lab. That is a very common type of solution, okay? However, we can also make solutions involving gases, okay? So the next thing we're going to talk about is the solubility of gases. And this might sound a little weird, but this is something that's very practical. I have some soda water here. It's red because there's some cranberry juice in here, but it's soda water. There's bubbles, right? So my soda water is my solution. My solvent would just be the water. Right, but what are those bubbles that are produced? Carbon dioxide is the solute in soda water. Okay, so we absolutely can get gases to dissolve into our solvents as well. All right. There are certain factors that affect the solubility of gases. Okay, one important one is pressure. All right, the solubility of a gas increases with increasing pressure. Okay. This has an important name. There's a scientist who sort of established a direct relationship here between these two, which is called Henry's law, which says that the solubility of a gas is equal to some constant times the pressure of that gas. Okay, so the S here is our solubility. The KH is our Henry's constant. And the P here is for the pressure of the gas. Okay, and so you can see, regardless of what that constant is again something that you could look up in one of those giant books or now more practically on an online database. It's different for every gas, okay? But what you can see is regardless what that value of KH is, if I increase the value of P, if I increase the pressure, the solubility is going to increase as well, right? So that's a phenomenon that's true for all gases, okay? So let's look at two different gases here. Nitrogen gas and ammonia gas. And we're going to look at their value for the Henry's constant. Okay. Our book has these. You can tabulate these in quite a few different units. Our books, so if you look online and you see different values, just pay attention to the units. Our book has them in molar per ATM. Right? So the solubility will be measured in molar and the pressure of the gas in ATM. Okay? So looking at these two gases here, if we were to dissolve these two gases into water here, which one do we think would have a higher Henry's constant? Right? If we kept the pressure the same, which one do we think would have a greater solubility? Nitrogen gas or ammonia gas? Daily quiz question 2. The ammonia, right? And why is that? Those polar hydrogen bonding interactions that it can make with water, right? Nitrogen, not a polar molecule, will only have those very weak dispersion forces, and so that's reflected in the value for the Henry's constant, right? So the value for the Henry's constant for nitrogen is 6.1 times 10 to the negative 4, whereas for ammonia it's quite higher, 5.8 times 10 to the 1. Okay? So then, I mean, it's a pretty straightforward equation here, but for the sake of practice, let's go ahead and use it real quick. All right, at sea level, the partial pressure of nitrogen, which is like where we are right now, right? So in this room right now, the partial pressure of nitrogen is going to be about 0.78 atm. The air that we breathe is actually made up of a majority nitrogen gas. Oxygen's the component that we need to stay alive, but majority of what's around us is actually nitrogen gas. All right? So if we had a cup of water here right now, let's see if we can figure out what the solubility of that nitrogen gas would be using this equation. So everybody take a minute and calculate what the solubility of nitrogen gas would be at room temperature, or at our, not room temperature, but room pressure. All right, so I'm just going to grab my Henry's constant from my table. This is going to be one of the tables on our constants page. For nitrogen gas, that's 6.1 times 10 to the negative 4, right? And this is molar per ATM. And I'm going to multiply it. Squeeze this over here. By that partial pressure of 0.78 atm. So this gives me 0.0004758. Not a big number, right? As you would expect for something that does not interact very strongly with water. All right, nonetheless, there is some nitrogen gas that will dissolve. You have a cup of water, you're drinking a little bit of nitrogen gas along with it, all right? Let's think sig figs here, because it's been a while. Actually, let's do units. Units are going to be a little bit more straightforward here. What are the units of my answer? All right, what happens to these ATMs? They cancel out, so I'm left with that big M, molarity, which we will also be reviewing here in a moment, okay? And then sig figs, my table is tabulated to 2 sig figs. My partial pressure has 2 sig figs. This was a multiplication problem. So what am I going to round my answer to? How many sig figs? 2. All right, so 0.00048 molar. Okay. Has anybody ever gone scuba diving? Cool. Yeah. I forgive y'all. There's not really many great scuba diving places here in Fresno, but it is very cool. All right. But one of the things that you learn is about what's called the bends, which is when you go down under the sea level, the pressure rises significantly. So the gas that you're breathing in is at a much higher pressure. And this can become dangerous because that gas, the nitrogen that you're breathing in, will now be more soluble in your blood. And then you go back to sea level and it starts to bubble out, okay? And bubbling blood is not a good thing. So they have these safety procedures in place for that, right? So the bottom line is when you increase that pressure, you're increasing the solubility of those gases, okay? Cool, all right. One more effect here, and we don't have a cool quantitative way of measuring it, but it's still important, is the effect of temperature on the solubility of a gas. Whoa. Okay, so if we have a can of soda and we open it up, right, it's going to go flat eventually because all that carbon dioxide leaves. Okay, does anybody have any practical experience? Does your soda tend to go flatter on a very hot day or when it's really cold? When it's hot, right? So it turns out that the effective temperature is the opposite of that of pressure. As the temperature increases, the solubility of a gas will decrease. Okay, so increasing temperature decreases the solubility of a gas. That's one of these concerns with rising sea level temperatures, is there are some gases that have been dissolved in these oceans that will become less soluble and be released into our atmosphere as those oceans warm, right? So as temperature increases, the solubility of a gas will decrease. And the thing is at temperature, things move around more. Those gas molecules are able to collide and form little bubbles and escape. So for gases, it's an opposite sort of trend as what we saw for solids.